So we're now up to the 18th lecture of the Condensed Matter course, and over the last couple weeks, we've been building up our knowledge of how to understand electrons in solids. We know about band structure, we know about electrons in holes, we know about effective masses, we know about doping. And at this point, we actually have arrived at enough knowledge that we can actually think about putting together materials in order to make real devices, and in particular, semiconductor devices. Semiconductor devices, which is in some way the crowning glory of the entire field of condensed matter physics. It's because we can make semiconductor devices that we can build things like computers, we can build cell phones, we can build iPads, and all these other things that we take for granted and completely change our, the way we live these days. It's all because we understand semiconductor physics extremely well. The good news is that it's totally non-examinable. But that means that we can't, the bad news is that means we can't spend a whole lot of time on it. Even though it's an extremely interesting subject, you could spend the rest of your entire life studying semiconductor devices and building new ones, and probably some people in this room really will. The semiconductor industry is a huge industry that employs many, many physicists, so people will be thinking about semiconductor devices in the future. I promise you, someone will. But for us, it's going to be limited to about 40 minutes. But we'll see how far we can get in 40 minutes. So the simplest semiconductor device we're going to discuss is the quantum well, which is nothing more than a sandwich of one material inside another material. So you imagine having a three-layer material. Over here, over here we'll put aluminum arsenide. Here is gallium arsenide. And here's aluminum arsenide. So it's a thin layer gallium arsenide in between aluminum arsenide. This is X, some position coordinate. And we've actually studied this material before, gallium arsenide. And remember, it has a zinc blende structure. It's FCC with the basis. Aluminum arsenide is just like gallium arsenide, except you replace the gallium with aluminum, so it's also FCC with basis. And the reason that I've chosen these materials, aluminum arsenide and gallium arsenide, is actually there's a little bit of a gift of nature here. It turns out that the lattice constant, the size of the unit cell for gallium arsenide and aluminum arsenide, is extremely, extremely precisely the same. It's just something that randomly occurs, which makes these very desirable materials to work with. The reason that makes things very desirable is it means that you can line up the atoms directly between the gallium arsenide and the aluminum arsenide and basically have just one giant crystal. And as you walk through the crystal, the only thing that changes is in going from this material to this material, all the aluminums get secretly replaced with galliums. Okay? So it just looks like one big crystal of one material, but over here you have aluminums, here you have galliums, and then you're back here and it's aluminums again. The difference between the different materials is that the band gap in aluminum arsenide is actually bigger than the band gap in gallium arsenide. So you might have a band structure that looks like this. It's a big band gap out here, small band gap here, big band gap here. So if we plot the conduction band energy, E conduction, it will be big here, then it drops down in this region here, which is known as the quantum well, and then it comes back up over here. So this is the aluminum arsenide, here's the gallium arsenide, and here's the aluminum arsenide. So if you're an electron living in that conduction band, what you see is you basically see a well, some sort of confining potential like a particle in a box, and you would form a wave function in that particle in a box in the usual way. And of course, you could have excited state wave functions also in that particle in a box also. The only difference between this and the kind of particle in a box problems that you solved in your quantum mechanics courses is that it's m star, not m. The effective mass of the electron is important. The effective mass of the electron in the conduction band is the important thing that shows up in the Schrodinger's equation, not the real mass of the electron. And the other thing that's different is that this V of x, this potential, is actually due to the band structure. Due to band structure. So that's what's causing the potential to go up and down, that the bottom of the conduction band is moving up and down. Now, if you think about the valence band, it actually looks the opposite. The valence band, E valence, the top of the valence band starts low, goes up high in the middle, and then comes back down like this. And if you were a hole living in the valence band, remember that holes try to go up instead of coming down, like electrons try to come down. So in fact, a hole can get stuck in this sort of upside down well, and it would also form a particle in a box wave function inside this quantum well. So you can trap both an electron up here and a hole down here. Now this very simple structure is actually used quite frequently in the semiconductor industry, very frequently for making lasers. What happens is you imagine putting an electron up here and a hole down here, and then the electron can fall into that hole while emitting a photon. It comes out, and if you learned some laser physics last term, you understand how if you have transitions like this, you can build lasers out of them. The thing that's neat about this structure is you can change the energy of the eigenstates by changing the width of the well. So if you make it a thinner layer inside this of gallium arsenide inside aluminum arsenide, then the energy eigenstates change, just because the energy eigenstates always depend on the width of the box. And so you can tune the energy of the outcoming phonon by just changing the width of the well. And that's why this kind of device is frequently used in optoelectronics. Okay? All right, so this is the very simplest device that we ever need to think about. We don't have to worry about any dopants. Now we're going to think about adding dopants, which when it will enable us to make some much more complicated devices. So doping, and although I said at the beginning of the lecture the semiconductor device is not examinable, doping is examinable. We discussed this at the end of last lecture. I'll remind you of some of the results. That if we dope a semiconductor, the density of electrons in the conduction band is some constants, which I won't write down, times an exponential factor, e to the minus beta E conduction minus mu. So basically, the big part of this, the exponential factor, tells you that you have to activate an electron up into the conduction band from the chemical potential. It's exponentially activated up into the conduction band. Okay? And then there's a couple of prefactors out front which aren't that interesting. Similarly, and actually it should be clear that as you raise the chemical potential towards the conduction band, the density of electrons in the conduction band goes up. Similarly, if we want to know about the density of holes in the valence band, P, that's some constants also, e to the minus beta mu minus EV. So similarly, we have the holes being activated down into the valence band, because remember, it requires energy to push a hole down into the valence band. The holes want to bubble up. And again, it's activated. If you move the chemical potential down towards the valence band, then the density of holes goes up. The law of mass action tells us that the product of these two things, N of T, P of T, equals, and there's a couple of these two sets of constants, then this e to the minus beta E conduction minus E valence. And this is independent of the chemical potential. So what one should take away from these equations for, which have to do with density of electrons in the conduction band and density of holes in the valence band, is that if dope heavily with N, in other words, add a lot of donors, then chemical potential goes up to the conduction band energy. It goes up towards the conduction band energy because we have to raise the number of electrons while keeping the product here fixed, and the only way that happens is by raising the chemical potential. Similarly, if dope heavily with P, with acceptors, adding holes to the valence band, then mu goes down to the valence band energy. Okay? Is that much good? That's everything that's examinable about device physics, is these two boards right here. So now what we can do is we can think about what happens if we put some dopants in our semiconductor. And this brings us to our first interesting device, which is the p-n junction. P-n junction, which was surprisingly discovered, or essentially discovered, in 1874 by Ferdinand Braun. Ferdinand Braun actually had no idea what it was he discovered, but he was a clever enough physicist to realize that what he had discovered was really interesting. In fact, it became an extremely important thing. It was a little electronic widget that enabled the development of the radio. Without Braun's discovering of this device, we wouldn't have been able to build a radio, and of course the radio is one of the inventions that really changed communications and changed the world in many ways. So p-n junction changed the world back in the 1800s or beginning of the 1900s. But actually, it wasn't really understood why the p-n junction behaved the way it did for about 70 years after Braun's discovery. So let's see if we can understand what it was that Brown didn't understand. So first of all, what is the structure? So you start with a big piece of semiconductor, and you just p-dope one side of it, and you n-dope the other side, n-dope the other side. Now, when Braun actually built this, he took two pieces of materials and just stuck them together. In the modern era, you take one big crystal and you add some dopants over here and you add some dopants over here, much more controlled than what Braun did, but generally the same idea. And so let's draw a picture of where the conduction band and the valence band are. So the conduction band energy might be up here. The valence band energy might be down here, E valence, down here. And here's our division in the middle. Now, over on this side, we're n-doped. So that means we have a bunch of electrons up in the conduction band here. And the chemical potential is way up here, mu, up here near the conduction band because we've doped it with the electrons. So the chemical potential went up towards the conduction band energy. Good? Now, over down here, we have a bunch of holes in the valence band. And the chemical potential has been pulled down to near the valence band energy. So far, so good? All right, now the way it's drawn, this looks like you have negative charges on the left and positive charges on the right. That's not actually true because we left out the charges on the nuclei. So the nuclei have charges also, nuclei, nukes, and they have compensating charges like this and compensating charges over here. Because you remember when you add for example, when you add a phosphorus to silicon, you add an extra nuclear charge. You also add an extra electron. The whole thing is neutral. The electron goes off into the conduction band, but you left a positive nuclear charge behind as well. So everything here is electrically neutral, no electric fields. The electron negative charge is compensated by the nuclear positive charge, and the whole positive charge is compensated by the acceptor negative charge here. So far, so good. OK, now, here we have electrons up here in the conduction band, and we have holes here in the valence band. And in fact, this electron, if he falls down to the valence band, annihilating its hole, he can let off energy. He can emit a photon, for example, and lower the energy. So what happens is, erase that, the electron here, a little bit of eraser transform, annihilates the hole, electron annihilates the hole, and you end up with a region. Let me annihilate one more here. Annihilate one more. And we end up with this region in the middle from here to here, which is known as the depletion region. Depletion region, where there are no electrons and no holes. There's no mobile charge carriers anymore. You only have the static nuclear charges left. Okay? Nothing moving around. So you might think that this annihilation would keep going because the electrons are up at high energy and the holes are down at low energy. So we can just keep annihilating electrons with holes, keep emitting photons, and lower and lower and lower the energy. But that's not true. In fact, it doesn't keep going. And the reason it doesn't keep going is because we're leaving a net charge behind. This region now is charged. This is net positive charge because of the dopants, and this is net negative charge. Net minus charge. So as we start annihilating, we leave actually a charged region here and a charged region here. And that means we have an electric field. I guess the electric field points from the minus to the positive. And minus to positive, positive, negative, which way? Let's see, the direction of a positive charge goes positive, negative. Points this way, yeah. Electric field goes from positive to negative. Test charge goes towards the negative. Yes, OK, got it right. So there's an electric field here that we're building up. And as we annihilate more charges here, we end up with more and more electric field. And that means if we want to take one more electron here and annihilate one more hole here, we first must climb up a potential hill, an electrostatic potential hill, to get past this electric field to reach the hole here. At some point, this electrostatic potential hill becomes too big, and we can't get over it, and we can't have any more annihilation. So the depletion width is set by setting the gap energy, E gap, the amount of energy you would gain by annihilating one more energy with one more electron with one more hole, has to equal to E times delta phi, the amount of energy you have to put into it to get the electron over the electrostatic hill that you're fighting against to move the electron past the, this charged region. Is that clear? Roughly? Someone? Yes? OK, good. At least someone said yes. And this potential here is just the integral of E dot dl from, well, across the system. All right, so generally, we don't believe that this depletion width is going to be infinitely big. It's going to stop at some region. But this is not a good way to draw what goes on, because this looks a little, strange. It looks incorrect. I mean, it looks like the electron here is at higher energy, and the hole is at lower energy. So it kind of looks like the electron should still want to annihilate the hole, but we know that there's an electric field that's making it difficult. So what we want to do is we want to redraw this picture in a way that will make it obvious that the electron doesn't want to come and annihilate one more hole. So what we do is we draw things in terms of the so-called electrochemical potential. Electrochemical potential, which is the combination of the regular chemical potential and the electrostatic potential. Okay, so we're going to plot that instead, which is going to combine together the sort of the band structure diagram as well as the Coulomb effects of the space charge that we left behind. So over on this side, we'll draw the same picture we had before. So we have the conduction band energy up here. The electrochemical potential we'll put here. So this is mu minus E phi over here. We have the valence band energy over here, E valence. Now over here, on the other side, we are going to line up the electrochemical potential exactly the same. But here, the valence band energy will be here, E valence, and the conduction band energy will be up here, E conduction, and these get connected together like this. Okay, those are supposed to be parallel lines, not very parallel. Should I improve it? Yeah, let me improve it. Raise this up a little bit more. So they look very vaguely parallel. So these are supposed to be parallel to each other. Okay, good. So all I've done is I've taken that picture up there and I've twisted it. I've sort of bent it so as to account for the additional electrostatic potential. So now on the left and the right, the electrochemical potential lines up with the electrochemical potential over here. And what that tells us is that there's no net driving force for moving an electron from this side to this side. That there's a change in the chemical potential, but there's equal change in the electrostatic potential that compensates it. So the left-hand side and the right-hand side are completely lined up as far as the electron is concerned. It doesn't want to move to the left. The electron doesn't want to go to the left. It doesn't want to go to the right either. It just wants to stay put. So this is the equilibrium situation. Is that sort of clear how this has been drawn? OK. All right. That's a terrible picture, isn't it? OK. But this device here, this is basically the physics of the p-n junction. And even as it stands, just like that, without doing anything further, it's an interesting device because it's basically a solar cell, a solar or photoelectric cell. Photoelectric cell. And the idea of this is that you put in photons, get out current, get current. And this idea of putting in photons and getting out current is a $20 billion industry right now of people trying to build photocells that are going to replace our fossil fuels and potentially save our world from global warming and everything else. So I encourage all of you to go into the semiconductor industry and try to figure out how we're going to make solar cells more efficient so that we can get all of our power from these things instead of from burning coal and oil and things like that. At any rate, let's try to figure out why it is that this device has this property that if you put in light, you'll get out current. So if you put in light into this picture, you can excite an electron from the valence band up to the conduction band. So you leave a hole behind, and you excite an electron up to the conduction band from the valence band. Now, in this depletion region, there's an electric field. There's a strong electric field in this depletion region, and you can see it in this picture by the curvature of these bands. And what happens is the electron it's pushed by the electric field in this direction because it wants to go down to lower energy, and the hole is pushed in this direction, wants to go up to higher energy because holes always try to go up in the band structure. And either way, this is always current going to the right. It's either positive charge going to the right, this is plus going to the right, or negative charge going to the left, and both of those are current in the same direction. So just by putting in a photon here, which creates this excitation, you manage to create current. So this is the physics that's going to save us from global warming one of these days. So please, go off into the world and figure out how to build those better. They're still not quite as cheap as burning fossil fuels, so people aren't willing to use them yet, but maybe someday we will. Okay. This is not what Ferdinand Braun discovered in 1874. What he discovered was something was the same device, but he discovered another effect that these things have, which is maybe equally interesting, which is the effect of rectification, which means that current flows one way, but not the other. And if you're good with your circuits, you might be able to figure out why it is that having something that with this property, which rectifies, enables you to build a radio, which is what he realized very quickly, that if you have something that rectifies, allowing current to flow one way but not the other, you can build a radio with it. So why is this? Why does it have that physics? So okay, let's take this device and let's imagine, well, let me draw the same picture again, except what I'm going to do now is I'm going to put a voltage across this picture to try to get current to flow. So let's do that. Draw exactly the same picture. EC, here's the electrochemical potential, mu minus E phi on the left. And then down here is the valence band energy, E valence. And then over here, instead of lining up the electrochemical potentials exactly on the left and the right, I'm going to shift the chemical potential down, the electrochemical potential down here. So this is if it was lined up exactly. It would be exactly the same, lined up here. And now I'm going to shift it downwards by EV here, by some energy. So this is the electrochemical potential on the right. So now, because I'm putting a voltage across the whole thing. So then we have to put in the valence band energy, I guess, mu minus E phi here. Is here, and the valence band energy is here, E valence, and then the conduction band energy will be up here. Conduction, then in the depletion region, you have electric field, which connects these together like that. Okay, so is it clear what I've drawn here? I've taken exactly the same picture. I've just applied a voltage across the two to shift this chemical potential down to here. Good? All right. So now that I've applied this voltage, how much current flows? Well, there's several ways you can get current. One way to get current, let's call this process 1, is that an electron in the valence band could get excited up to the conduction band and then eventually find its way down the hill. Okay, so let's call that process 1. And process 2 is sort of the reverse of that, which is the hole up in the conduction band could get excited down into the valence band, because remember, it requires positive energy to push a hole down into the valence band, and then find its way up the hill. So process 1 and 2, that's either an electron going to the left or a hole going to the right, and either way, its rate is e to the minus beta E gap, because the limiting step is to get the electron up into the conduction band or get the hole down into the valence band, and that costs you the gap energy, so it's activated. Okay? So that's one thing that can happen that can cause current. But another thing that can happen that can cause current is you have some number of electrons up here in the conduction band already, and they could just climb up the hill. Let's call that 3. Or we have some holes here in the valence band, and they can just climb down the hill. Let's call that 4. So 3 and 4, we have electrons going to the right, or holes going to the left, and they happen at a rate of e to the minus E gap minus EV. Why is that? Well, the height of this hill from here to here is E gap minus EV. If we had not applied this EV, it would be exactly the same gap energy that we would need to climb up the hill, but now we've reduced that hill, we reduced the size of the hill by EV, by applying the voltage across the system. So the total current, total J equals, well, it's going to be a combination of these two things. I'll call it A12 e to the minus beta E gap minus A34, those are just coefficients, e to the minus beta E gap minus EV, which, okay, then we need to know what these coefficients are, but actually there's sort of a trick for that the current, when there's zero voltage, should be zero. If you don't apply any voltage to the system, you shouldn't get any current. So that means A12 and A34 should be equal. So J is proportional to e to the minus beta E gap, factor that out, times e to the EV over KBT, that's beta EV, minus 1. Okay? So this is what's known as the diode equation. Diode equation. The p-n junction, or the rectifier, is sometimes known as a diode. And we can plot its behavior over here. So we have current, voltage on this axis and current on this axis, and it's exponential in the voltage. So this is zero current here, and this is negative current here. So maybe I should have drawn it like this. Zero is here, and negative is here. So with positive voltage, it goes up exponentially, whereas negative voltage, it goes to a constant, which is an extremely small constant. So this is frequently drawn figuratively as being straight up like this and straight flat like this, which, you know, we approximately say it allows current to flow in one direction and allows no current to flow in the other direction. Frequently, we draw in a circuit diagram, we draw a diode like this, diode, which means current flows only in one direction. Okay? It's a pretty neat device to put into your circuits when you're designing circuits. So this was what Ferdinand Braun discovered experimentally, more or less. And it wasn't understood until the 1940s when people really developed a good understanding of semiconductor physics. And by that time, when they finally understood semiconductor physics, they realized they could do a lot more with it than just building diodes. And this enabled them to start working on the next big invention that changed the world, which is the transistor. Invented in 1947 by the Bell Labs team of John Bardeen, Walter Brenton, and William Shockley. Bardeen is definitely a name that everyone should know because he won 2 Nobel Prizes, one for the transistor, one for the theory of superconductivity, a very bright but pretty much unknown person. And this device, the transistor, is the elementary, the smallest piece, the elementary piece, the building block of every computer ever made now. It's in your average cell phone or laptop or iPad. There are billions of these transistors sitting, literally billions of them in there. It's the elementary switch or elementary amplifier that enables everything to work. So transistors come in many different varieties. The one we're going to discuss is actually known as the MOSFET, which stands for metal oxide semiconductor field effect transistor. And I'll explain what that means as we get to it, although I should comment that the original transistor that they built in 1947 was not of this design. They were aware that they could build this design, but for various reasons they decided that was not the one they were going to try to build first. This is the type of transistor that's used most frequently in circuits now, so that's why I'm explaining that one. It's also easier to understand. It makes it nicer to talk about. The way it works is a fairly simple device. You take a big piece of semiconductor and you p-dope it, and it has a surface like this. You could do it backwards. You could n-dope it if you wanted to, but let's imagine it's p-doped. And then we take 2 small regions, and we n-dope them. Let's make it a little bigger. This region here, n-dope this region here, and then we'll n-dope this region here, this. And this is all p-doped. Okay, so what we have now is we have a surface with an n-dope, n-dope, and a big bulk with p-doped. We'll put contacts here on wires coming in. This is what we call a source wire, and this is called the drain wire. Drain. And then we try to run current from the source to the drain. Now, if you look at this structure here, you'll realize that current is not going to flow from the source to the drain. You'll have a depletion region at the interface between N and P. There's an NP junction there, and PN junction here. And one of the PN junctions wants the current to only flow one way, and the other one wants it to flow only the other way. You can kind of think of it figuratively as being, two back-to-back diodes pointing in opposite directions. So one of them only allows the current to flow to the left. The other one only allows the current to flow to the right. So between the two of them, you can't get any current through it at all. Okay? So this looks like a boring device. But now we add the last part of the device. We put a big piece of metal on top like this, which is known as the gate. Like that, metal gate. And then we attach it to the source via a little bit of battery here. So voltage plus battery like that, attached to the metal gate. And then we put an insulator in between here, which is usually an oxide layer. And this is what gives the name of the device, metal oxide semiconductor. So the gate is metal, the oxide is in the middle, and the semiconductor is on the bottom. The purpose of the oxide is just to make a small insulating layer so the metal doesn't touch the semiconductor. You can make it of anything you want. It's just typically made of oxides, which are very nice insulators, and they're easy to build. You could make it of any insulator you wanted to put there. You could make it of diamond. You could make it of, it could be just vacuum if you wanted. But the point is you have to have the metal not touching the semiconductor. So it's usually called metal oxide semiconductor. In fact, the gate doesn't have to be metal either. It just has to be conducting. So it can be whatever you want as long as it's conducting. At any rate, it's called metal oxide semiconductor because it's almost always made of metal oxide and semiconductor. All right, so what's the purpose of this metal? This metal gate, you charge it up so it has plus charges on it. And this plus charges act like a capacitor, and they're going to attract negative charges on the semiconductor here. Now, this region in the semiconductor, so we're basically just charging up a capacitor plate between the metal and the semiconductor. This region here on the top of the semiconductor, it used to be p-doped. It used to have holes there. But now we've attracted a lot of electrons into that region. So instead of being p-doped, it's now majorly n-doped because we just attracted electrons there, so now it's n. So instead of having something that looks like that picture I had originally, it now looks more like this. This whole region here, all the way from here to here, is negative, is n-doped, has electrons in it, and the depletion region sort of makes a big sort of environment like this. Now here you can get current directly from this n region to this n region via this electron channel. So you've added electrons to this layer so the electrons can travel directly from the source to the drain without having to go through a PN junction. That's the point. Okay? Is that good? Happy with that? All right, good. So the characteristics of such a device look more or less like this. That if you plot the current versus the voltage, this is the voltage between the source and the drain. This is the current that flows from the source to the drain. If you put no gate voltage on, V gate equals 0, you get almost no current flowing. But if you put a little bit of gate voltage on, V gate equals, say, 2 volts, you all of a sudden get a lot of source drain current. So this enables you to take a small voltage on the gate and control a very large current. So this is basically why this device is so useful. It acts as an amplifier. It can amplify a very small signal on the gate, and then you can do interesting things with it because now it's become a big current that you can work with. Okay? The elementary circuit, the element that builds all computers in the modern age. All right, well, I hope many of you will go on and study more semiconductor device physics, more than these last 35 minutes. But this is all we have time for in this course, unfortunately, and we have to move on to the final segment of our course. And the final segment of our course is sort of leaving all this stuff behind us, and we move on to study magnetism. Magnetism. So take a deep breath, and we move on to magnetism. And the first question one probably wants to ask is why are we studying magnetism, and why are we studying magnetism now? The whole course, pretty much from day 1 all the way up to lecture 18, halfway through, which is right now, we've really been studying waves in solids, one way or the other, whether they're vibrational waves or whether they're electron waves or they're X-ray waves. We've really just been studying waves in solids in one way or the other. And magnetism is a little bit different. We're not really studying waves in solids when we're studying magnetism. So why is it that we're studying magnetism? Well, there's a lot of reasons why we want to study magnetism. The first reason why we want to study magnetism is it's an effect that's been known about since antiquity. And, there are records of people knowing about magnetism 1000 BC in Greece, 1000 BC in China. They knew how to build compasses. And it probably predates that by thousands of years. Probably there were cavemen who knew about magnetism, stuck notes on their refrigerator. Anyway. But despite the fact that this effect was known about thousands and thousands of years ago, there was absolutely no understanding of it whatsoever until people understood quantum mechanics. And that's one thing that makes this very interesting. In fact, there's a theorem by Bohr and Van Leeuwen, known as the Bohr-Van Leeuwen theorem. Niels Bohr, I think everyone knows, but Henrika Van Leeuwen was one of his students. Leeuwen theorem. And the content of the Bohr-Van Leeuwen theorem is basically no magnetism without quantum. Without quantum. That nothing in classical physics can ever give you magnetism in any sense. So that's kind of an interesting statement. So it tells us that, that magnetism is a really good place to go to understand, the macroscopic ramifications of microscopic magnetism. So that's one of the reasons why we want to study it. Another reason we want to study magnetism is because it's a rather spectacular failure of everything we've been doing so far. That magnetism, the band theory we've been studying so far, would always predict that you have the same number of upspin electrons as downspin electrons. Whereas in magnetism, it's just not true. You have magnetic substances where you have a different number of spin-up electrons and spin-down electrons. It's completely outside of band theory, and it's completely not predicted. So magnetism is a way to understand the limitations of what we've already been doing. The final reason, which is maybe not so obvious, is that magnetism is a really great place to study phase transitions between phases of matter. So everyone's familiar with phase transitions between ice and water or water and steam, and you probably studied these things in your thermodynamics classes. But when one really gets down to understanding the details of these phase transitions, most of what we know about phase transitions comes from studying magnets, where things are much better controlled and much better understood. And much of what we know about the melting of ice into water, we actually know because we studied magnets. And then we sort of translated our knowledge into understanding ice and water. That's not an obvious statement. We will make some statements about phase transitions in this course. If you go on to study other courses, you'll learn a lot more about it. OK. So let's start by defining a couple of the types of magnetism that we're going to be working on, of magnetism, or at least some of the types of magnetism we're going to need to know about. Usually what we do is we apply a magnetic field to some object, and we measure a magnetization, M. And if there's a proportionality constant, we call the proportionality chi over mu naught, where chi is known as the susceptibility, or magnetic susceptibility. Susceptibility, I'm going to spell that wrong. S-U-S-C, susceptibility. Susceptibility. And mu naught is the usual magnetic permeability, the thing that's permeability, the thing that's on your data sheet in your exams. So given that as a definition, there's a couple kinds of magnetism that you can have. One is paramagnetism, which means, or a paramagnet, is any material with chi greater than 0. In other words, you apply a magnetic field, and you get a magnetic moment in the same direction as the field that you applied, which seems to make some amount of sense. And we know a couple of examples of that. Example 1 is a free spin. Probably studied this in statistical mechanics last year. If you have a free spin sort of sitting in outer space, if you apply a magnetic field to it, its energy is lower if the magnetic moment points in the same direction as the magnetic field, so the spin will try to flip over and point in the same direction as the magnetic field. Hence, the free spin is a paramagnet. Example 2, which we studied earlier in this term, is a Fermi gas, or an electron gas, which we studied in the Sommerfeld model, and we found what's known as Pauli paramagnetism. And there was some calculation which went along with that. It's basically exactly the same physics. You have a bunch of electrons, you apply a magnetic field, the moments of the electrons want to align with the magnetic field to lower the energy, but they can't all flip over because of the Pauli exclusion principle, so only a few of them flip over, but nonetheless the magnetization that develops is in the same direction as the magnetic field that's been applied, so this is a paramagnet, albeit a weaker one than the free spin, because only some of the electrons will flip over in the case of a Fermi gas. Okay? We'll say more about those in a little while. So another type of magnetism, which is common, is diamagnetism, which basically means chi is less than 0. In other words, when you apply a magnetic field, the magnetic moment wants to point in the opposite direction as the magnetic field. Now, we may not know any examples of that immediately, but there's something that's qualitatively similar that we do know. Qualitatively, like Lenz's law, which you may remember from first year E&M. Lenz's law, to remind you, if you have a loop of wire, if you apply a magnetic field to the loop of wire, currents will flow in that loop of wire to oppose the magnetic field. So you're developing a magnetic moment in the opposite direction of the change in magnetic field. A loop of wire, however, is not a diamagnet. The reason for this is because that you'll develop a magnetic moment, but eventually the current in the wire will decay and will go down to 0, and you'll have no magnetic moment left in the wire. So in fact, it's not magnetic at all. It has no magnetic moment. Unless the wire is a superconductor, which has no resistance, so currents never decay, and the current would keep flowing around forever and ever and ever, and the magnetic moment would stay there forever and ever, and that's a real diamagnet. We don't study superconductors this year. It's just nice to know that you could do this with a superconductor and you'd get a real diamagnet. Anyway, the physics of diamagnetism is actually quite similar qualitatively to the physics of Lenz's law, but when you add quantum mechanics to it, you kind of, in some interpretation, you can think of these currents as being stuck there forever and always opposing the magnetic field, even when with Lenz's law, you have to keep changing the magnetic field to get the current to keep flowing. In a diamagnet, as long as the magnetic field stays on, the current should keep flowing. So we'll see how that happens in a bit. Okay? The third case that we need to know about is the case of a ferromagnet, which is when magnetization is not equal to 0, even when B equals 0. Something like iron has this property, the thing that sticks to your refrigerator. This is the thing that we usually think of as a magnet when we think about magnets. So a good place to start our study of magnetism is one atom at a time. So we'll start with atomic magnetism. And we'll build up to a magnetism of real materials. And I should put in this caveat that we always we will ignore the magnetism of nuclei altogether. And the reason why we ignore the nuclei is that if you think about the magnetic moment of some object, it's given by the Bohr magneton, where 2m of the object. For an electron, this is roughly up to the g factor. This is the magnetic moment of an electron. It's similar for a nucleon, a proton or a neutron, but the mass that enters in here is bigger by a factor of 1,000 or 2,000 or something. So that the magnetic moment that you get from a nucleus is much smaller than the magnetic moment you get from electrons. And that's why we're usually not concerned with the magnetism of nuclei. It is there. It sometimes turns out to be important, especially if you're thinking about things at extremely low temperatures or if you're looking at very, very subtle and fine effects. You do have to worry about the magnetism of nuclei. But for us, we're only going to be worried about the magnetism of the electrons because it's just much bigger. Okay? So we're going to ignore the nuclei. And then we have to start the way we always start, by writing down a Hamiltonian for the electrons in the atom. So I'll write the Hamiltonian. Hamiltonian, and it's conventional to use sort of a script H for the Hamiltonian, so you don't get it confused with a magnetic induction H, you know, B and H and mu and that kind of stuff. So we use a script H for the Hamiltonian. And we'll write it in hopefully ways that you've seen before. So there's a kinetic term, P plus EA squared over 2m, where A is the vector potential. Del cross A is B, whatever magnetic field I decide to apply to the system. Then there's going to be, so this is just the kinetic energy. Then there's going to be an attraction to the nucleus, V of R. And the last term we've seen before, G mu B, B dot sigma. And this is the Zeeman term. Zeeman. 2 n's maybe? 1 n? Anyone know? 1 n? Thank you. Zeeman term is my notes. My notes don't say it. OK, I don't know. All right. So this is the term that tells you that the magnetic moment of the electron is lower energy if the electron points in the same direction, if the magnetic moment points in the same direction as the magnetic field. This gets very confusing. The signs get very confusing here. Remember that the magnetic moment of an electron spin points in the opposite direction of its magnetic moment because the charge on the electron is negative. OK? So it looks as if the energy would be lower here when the, so here the energy is lower if sigma is in the opposite direction of B, so it's pointing in the opposite direction, so it's negative. But if sigma is in the opposite direction as B, the magnetic moment is actually in the opposite direction of sigma, so the magnetic moment is pointing in the same direction as B. I know minus signs are, you know, the death of me. OK, mu B is the Bohr magneton for the electron, and G is the G factor, which we'll usually take to be just 2. All right, so what do we do with this? Well, we really would like to treat the magnetic field a little bit as a perturbation, if we could. So, you know, we'll start by rewriting this Hamiltonian as in the following way: H equals P squared over 2m plus V of R. And that is just H0, or H of B equals 0. We'll separate out that term first. Then we have a couple terms left over that we didn't write yet, so maybe let's write those here. Plus all this stuff that we're going to write next. So one is the cross term with the vector potential, E over 2m, P dot A plus A dot P. And then there's another term, the vector potential squared over 2m A squared. And then we have the Zeeman term left over, G mu B, B dot sigma. And then we have to do a little bit of work here. One piece of work we need to do is we need to sort of simplify this term. And the way we're going to simplify that is by choosing a gauge. Choose gauge for the vector potential. And the gauge I'm going to choose is that the vector potential is 1/2 B cross R. And if you choose it like that, this does give you del cross A equals B. If you choose it like this, then A and P actually commute through with each other. And it's maybe not so obvious to see that that's true. But it is true because the X component of A contains the Y component of R. So the X component of A commutes with the X component of P. And those are the ones that are multiplied by each other. So it doesn't matter which order you put them in. So choosing this gauge, we can then rewrite this as E over 2m 2A dot P. So those two commute right through each other. And then we'll write in our expression for A. Well, we'll cancel the 2 with the 1/2. And we get B cross R dotted with P. We'll use a triple product identity to rewrite that as E over 2m B dot R cross P, And then just absorbing a factor of H bar into the R cross P, we'll recognize this thing as in the angular momentum and put the H bar up here. So we get mu B and B dot L, where L is the orbital angular momentum, equals orbital angular momentum. So putting this all together, we end up with the final Hamiltonian that we're going to work with. the Hamiltonian is the Hamiltonian at b equals 0 plus a couple terms, mu b, b dotted with the orbital angular momentum plus g times the spin angular momentum plus this one more term that we're left out, e squared over 2m a squared. And I guess maybe we should stop there and pick up next time with this Hamiltonian, and we'll analyze the effect of the magnetic field on this Hamiltonian. Okay, see you tomorrow. Don't forget the meeting right after the lecture for PJCC, and then also the Heinz lecture this afternoon at 5 p.m. searching for extrasolar planets or something. Okay, bye.